Okay.
We only know very small bits about this theory. We know some corners like heterotic string, 11D supergravity, type 2 string theories, type 1 string theory. But really, the big problem, you know, when you're writing a theory, when you're writing down a theory, usually you need an organizing principle. For example, if you start from perturbative gravity and then you wanted to guess the structure of non-perturbative Einstein-Hilbert action, like
Hmm.
not perturbative in the gravity, weak field expansion, I'd be very surprised if you can just guess the structure of the Einstein-Hilbert action by just doing more and more perturbative calculations. You need more input. For
Hmm.
example, you need to understand the symmetry structure or some organizing principle. I really think we do not know what that is. Of course, some naive hope that I have is that, for example, string theory or string perturbation theory is famously asymptotic. And by that, what I mean is that by doing more and more perturbative calculations, we'll understand more and more about what kinds of non-perturbative effects that we need to include, and then that might lead to some hints.
The guest of today's podcast is Dr. Manki Kim. He is a theoretical physicist at Stanford University working on string perturbation theory and string compactifications. He has also worked on string field theory. So let's talk to Dr. Kim about his work in physics and listen to what he has to say. So, Dr. Kim, welcome to the podcast. Nice to have you.
Hey Hassan, thanks for the invitation. I really appreciate it.
My pleasure. Okay, so before we talk about anything else, can you tell us a bit about some of the projects that you're working on nowadays?
Oh yeah, good. Where should I start? Yeah. So the big question I am curious about is whether or not string theory can really describe our universe. Of course, it'd be amazing if we can describe everything, including particle phenom and cosmology, but I think that's too ambitious of a goal. So my hope is to first address cosmology, early universe cosmology and late time cosmology. And to do so, I think one big question that we really need to understand is whether or not it is possible to construct some solution like de Sitter in string theory. It can be de Sitter or it can be like quintessence, but anything that looks like our universe that is also theoretically well controlled. And what we've been beginning to understand bit by bit is that if you really want to, say, construct a solution like de Sitter, there is no parametric control. And to do so, what that means is that once you have found a solution, you really don't really know whether or not some corrections that you are not able to compute are large or small enough. So what I've been focusing my time on is to understand how to compute such corrections, um, in particular in the context of Raman-Raman backgrounds and using string field theory to compute some of those corrections. Yeah, so I think I can summarize my current projects as that.
Right. So I'm sure you know about this, study from Daisy that came out a while ago that suggested that, the cosmological constant may be changing, which means that, quintessence models may be better suited to describe what's going on out there. So
Mhm.
uh, do you do you know about a lot of quintessence models built out of string theory that people are working on?
Yeah, unfortunately, I think, well, although there are many proposals on how to construct quintessence-like models, I don't think we really have any concrete solution or candidate solution or very concrete proposal that actually gives you some phenomenologically viable quintessence model. And it might be due to my uh, s- uh, lack of knowledge, though. The reason why it's quite difficult to construct a quintessence is that, well, if you just want a crappy quintessence, well, maybe we shouldn't even say quintessence for the crappy quintessence. Then it's really easy to make because the only thing that you need is a rolling potential that is flat enough. But if you really want a phenomenologically viable quintessence model, then things are getting really, really difficult because not only do you need, well, then the requirement on the flatness of the potential, and at the same time the value of the potential must be really, really small. And the flatness is really, really difficult to guarantee unless you are really good at doing some calculations in string theory. So yeah, the answer is that I do not really know of a good model or a good candidate solution that really achieves the phenomenologically viable quintessence model. It doesn't mean that there cannot be one. It just shows our lack of imagination and our lack of abilities to compute things in string theory. Maybe I should say that way.
So I'm not very familiar with the quintessence models that come out of string theory, but one question that I have in mind is that do you know about any? So are there any no-go theorems when it comes to quintessence models? For example, when we talk about getting a particular cosmological constant from string theory constructions, we do know that there are some no-go theorems that prohibit you from getting a positive cosmological constant from very simple constructions. So do you know about any no-go theorems or any constraints that people have argued about that you can get from
Hmm.
string theory, or are there no such no-go theorems for quintessence models?
Yeah, I'm not really aware of a strong no-go,
Hmm.
and I don't think it'd be hard. I think it'd be hard to find such a no-go because,
Hmm.
in string theory we have rolling potential. So if you broaden your definition of quintessence, it's not really going to be possible to come up with a no-go because we already have good candidates, although they are phenomenologically quite crappy. Um, So if you really want to have a sort of no-go for quintessence, I think you need some phenomenological bound. By that, what I mean is that the bound on the value of the CCN at the same time, the bound on the gradient of the potential,
Yes.
a very precise numerical bound. And as far as I'm aware, there is no such a no-go theorem. And it'd be hard to come up with a no-go theorem like this, in my opinion. But yeah.
So, but when it comes to like constraints on the value of the potential and the flatness of the potential that you can get, you were saying that you were not aware of any bounds like that either. Is that
Yeah, of
correct?
course. Yeah, of course. We know that in the asymptotic limits, where string
Hmm.
coupling and the curvature are becoming smaller and smaller, we have some bounds like those.
Okay,
But aside from that, I'm not really sure.
I see. I see. Okay, so we're going to talk about some of the works that you have done in the past, but before that, I want to ask you that how did you get interested in physics? Because people have different routes to become interested in physics, so I want to know how did you get interested in physics?
Yeah. Well, when I was really young, as many kids, I was interested in those pop sci, but I really didn't invest much of my time in science and physics. I was more interested in playing computer games and video games when I was young. And then at some point in my life in middle school, I saw this big flyer saying that if you go to a science high school, you can stay in dorm. And that caught my eyes because I wanted to live in dorm away from my home. And then that's the moment I started really seriously studying science and math. And you know, I I thought it was quite fun to study math and physics. And the thing that really stands out for me in terms of like being fallen into love with physics is that it really explains many things. Starting from simple principles, it allows you to have a very amazing predictive power to explain universe and whatnot. Um, so that was really fun. And also, at least when I was young, I was good at it. I was better than other people. So I naturally started liking physics and math. Well, that doesn't really mean that why I chose my career in physics. Um, if I'm being quite honest though, I didn't choose physics as my career because I'm just genuinely curious about what's happening in nature, and I didn't have this innate desire to explain things with physics. What I really wanted is that, in Korea we have a saying like this: when tigers die, tigers live first, but when people die, people live their names. And what I really wanted is that when I die or something, I wanted to look back and think, oh, I've done something good, and I've done something fundamental, so that my name will be remembered. And then I thought, given my limited capability, the best shot of me doing that would be to do something meaningful in science and math, or doing research in science. Although, you know, as is same for everyone, the chance of actually making a very meaningful contribution is extremely low, but I thought maybe it's non-zero, although
Sure.
it requires a lot of luck.
Right. So would it be accurate to say that physics gives you, a meaning to your life?
Oh,
Doing physics gives you meaning to your life.
yeah. Well, I think there are many things that give meaning to my life, but yeah, I
Mhm.
guess physics indeed does give some purpose.
Sure, sure, sure. I mean, one of the things, since you have brought this up, I want to share one thing, one particular thought with you, and I don't know if you will agree with that or not. But the thing is that, it's hard for a lot of people to, find meaning in their lives. And, you have to, set up your own goals to, achieve, and that can give you some meaning. But those kind of things, as you can see, they're very subjective, right?
Oh
But
yeah.
if you can so I don't know if there is any way in which you can say that there is this objective meaning of life, but the only way that I can think of an objective meaning of life is that since we are made up of universe, and there is this quote by Carl Sagan which says that we are the way for the universe to know itself. So if we try to understand how the universe works, that's probably the only objective meaning that I can think of. So this is I think what you were saying is probably in that direction. Is that accurate or not?
Well, I think that's a very noble purpose to have, but I think what I actually sincerely desire is
Hmm.
very selfish. It's a very
Yeah, I
selfish thing,
understand.
not that noble. I just want to do something good so that people will remember me.
Sure, I understand. Okay, so you also mentioned, I mean, it's not related to physics, but you also mentioned that when you were young, you liked to play video games. What video games were you most interested in playing?
Oh yeah, there were so many video games I even forgot the names of. But of course, I played a lot of StarCraft. I played it
Mhm.
for too much time, perhaps. And when I was young, I was also very much into those games that you can shoot guns, like I
Right,
forgot the names of again, but something like Battlefield.
right, right,
Those
right, right.
games, yeah,
I see.
not very
Uh,
meaningful games.
sure, sure. So you said that, um, well, you didn't mention any particular book that you read when you were young that inspired you to do physics. Was there any book that you read that inspired you to do physics when you were young?
Like I read many science books and pop sci books, but really, no book really
Hmm.
made me really want to do science. Of course, those books made me curious about science and curious about physics, but I wasn't really fully convinced that those are the things that I really want to do, because those books were in a way too vague and too far away from
Right, right.
something that I can actually comprehend. So
Sure.
yeah, really the thing really that hit me was when I was more mature.
Right. So, was there any pop sci book that you read that stands out to you? I mean, that you like the most?
That's a great question, but somewhat funnily, I can actually say that Peter Watt's book on Not Even Wrong actually
Mm.
affected me during college. Um,
Probably that's
so
probably the last book that I would have expected, but okay.
Well,
That
because I really think some criticisms against string theory
sure.
mentioned in his book are fair in that we don't have any experimentally falsifiable predictions. Well,
I agree.
people can say that at Planck scale we have many predictions, but not
Mhm.
that is really far away. So yeah, those books, but as you can see, like I couldn't really think of any single book that really made me want to pursue a career in theoretical physics or
Mhm.
physics, really. Some books have good points and some books have some interesting points, but not really.
Okay. Okay, I see. Okay, so there is one piece of work that I want to talk about, and that you did with some of your collaborators in 2021 that has to do with small cosmological constants in string
Oh
theory.
yeah,
But
sure.
before I talk about that, can you explain, in your words for the audience that what is the cosmological constant problem? If you had to give a small summary of that.
Yes, cosmological constant problem is kind of like a fine-tuning problem. So let's suppose that very naively, um, so yeah, we have a very we have foundational pillars of modern theoretical physics. One is quantum mechanics, the other one is general relativity. Yeah. And then, of course, somehow when we're trying to combine them, they don't really like each other. And one major problem when you try to do so can be shown when you're looking at this one very particular sector of your theory or part of your action or whatever. That is called the cosmological constant. So the cosmological constant is basically like a constant that you can add into your Einstein-Hilbert action. And the problem is that when you compute the loop corrections to the cosmological constant, and then if you believe that your well, loop by loop corrections, I of course assume that we're doing some quantum mechanical computation, and then we assume that quantum mechanics somehow works well with gravity. And then if you assume that the quantum mechanical prescription that we're using works up to a fairly high energy scale, then the loop corrections to the, say, the so-called cosmological constant is just too massive. And if you just naively assume that your quantum mechanical procedure works up to the Planck scale, where we expect the quantum gravitational effects are expected to kick in, then roughly the loop corrections to the CC is like 10 to the 120 times bigger than the observed value of the cosmological constant. Then what you can say is that, okay, maybe although the loop correction is humongous, maybe the bare parameter for the CC that we started with was actually very so close to the loop corrections so that they somehow cancel each other, and then the true value of the CC is actually as small as what we observe in our universe. But this is rather weird, and we don't really understand why this has to happen. And this led to many confusions, or some people really believe that this is a big problem, or some people believe that this is an aesthetics problem. There is no reason for the bare parameter to be not very fine-tuned. But anyhow, this fact that the loop correction to the cosmological constant in your Lagrangian is so massive compared to the observed value, and we don't really understand how that fine cancellation occurs, that whole thing is called the cosmological constant problem.
Right. So, just for another perspective on this problem, can we say that the fact that cosmological constant is small is related to the fact that gravity is weak? Or in other words, Planck scale is big, same thing.
You see, even if you assume that the Planck scale or
Mhm.
the Planck scale or whatever is close to TeV
Mhm.
or weak scale or a few hundred GeV, the loop correction to the CC will still be too big
Still big.
compared to
Yeah,
the
okay.
CC.
I see. That makes
Yeah.
sense. So you said that cosmological constant is a constant that you add to, your Einstein field equations or the Einstein-Hilbert action. But we do know that although it's small, it's positive. So can you tell us a bit about the struggles that string theory has with producing a positive cosmological constant? And if possible, can you also explain that why is that the case? I mean, if that's easy to explain.
Yeah. That's a great question. There are quite a few challenges. The first challenge is that you see the positive cosmological constant in Lorentzian signature is not compatible with supersymmetry. And when we don't have supersymmetry, we're actually quite bad at doing any calculation in string theory, despite that we've been studying string theory for 50 years, which is a shame. But anyhow, that is one crux of the problem, that we're really bad at doing string theory without SUSY. The other problem is that there are not so many proposals on how to construct the vacuum out of string theory. And this is also tied to our lack of imagination and our poor understanding of string theory. So given the ingredients that we know about string theory, there is only a very limited options that we can think of to construct the solutions. The other thing is that supposedly there are so many different solutions and so many different corners in string theory to look at to hunt for digital solutions. Say that you want to start with a Calabi-Yau compactification. There are already gazillions of Calabi-Yau manifolds that you can choose. And in each Calabi-Yau manifold, there are so many different phases and different parts of the moduli space. And the problem is that when you want to find digital-like solutions in string theory, you need to also turn on the so-called Ramon-Ramon and NS-NS fluxes, and they'll also generate a plethora of vacua that you need to also search through. That massive number of different possible choices is a big problem because you need to understand where to look at. If you're just randomly looking at those solutions, basically the chances that you'll never find any solution. And the other technical challenge is that, as I mentioned previously, once you find such a digital solution, then one consequence of this is that all the moduli fields that determine the coupling constants in string theory are frozen to be some VAV. What that means is that you cannot take some parametric limit where the coupling constant is going to be arbitrarily close to zero. Once that happens, you need to make sure that all the corrections that we presently do not know how to compute are somehow under control. But tied to the first point that I mentioned, we're really, really bad at doing any general calculation in string theory without using SUSY. And unfortunately, those corrections that can actually affect the vacuum structure are not in general respected by SUSY. So we need to develop tools to compute general physical observables without relying on SUSY, but we've been relying too much on SUSY, which is really a big shame, so that even if you find a candidate solution, let's say, by overcoming all the hurdles, we don't know how to really compute those corrections, and this is a big problem. So I think those are the main challenges. Of course, there can also be a hidden principle that could actually forbid the solution in the string theory landscape. I don't really know of any principle like this, but that is also a logical possibility.
I see. So this 2021 work that I was referring to, you had two papers with your collaborators where you had a very small cosmological constant, which is smaller than 10 to the power of negative 123 in appropriate units, and but it was negative.
Mhm.
So how were you able to generate that small of a cosmological constant? If you can explain that in simple terms, you can use some jargon, of
Yes,
course. That's fine.
yes. Yeah. So I mentioned that there are some proposals, and despite the proposals, because there are so many different possible candidates, say a choice of Calabi-Yau, a choice of fluxes, a choice of, say, rentifolding, it is really difficult to actually find a solution that can realize some of the requirements put forward by some of the proposals. So in this particular context of this 2021 paper that you're mentioning, the proposal was put forward by Kachur Kalush and Linda Trivedi, and this proposal typically goes by the name of KKLT. And what KKLT tells us is the following. If you want to find a de Sitter-like solution in type 2b or F-theory compactification of string theory, here's what you need to do. First, in the context of type 2b, you find Calabi-Yau rentifold compactification with O3 or 7 planes. And then, once you have a rentifold compactification, your compactification preserves 4 supercharges in 4D. And in that theory, in that effective theory, the vacuum structure is determined basically by the Kähler potential, superpotential, and some holomorphic gauge couplings if you have some gauge theory setting. And now the goal is to use those ingredients to find a solution that can realize small cosmological constant. The goal is to find this, but let's first chop off some parts of the KKLT proposal so that we can actually focus on ADS. And then the Kähler potential, we know some things about the tree-level contribution. And the superpotential is something that we actually know quite well. The superpotential is a holomorphic function of moduli. And due to some non-renormalization theorem, superpotential is just written in terms of the tree-level superpotential, which is given by Kukov-Vafa-Witten superpotential. And the rest is just given by non-perturbative superpotential. So using the superpotential and the Kähler potential, you can write down the effective potential, the so-called F-term potential, and then KKLT observes the following thing. The tree-level superpotential depends on the so-called complex structure moduli and the axios dilaton. And the complex structure moduli, you can basically think of it as some moduli parameter that determines the shape of the Calabi-Yau. And the axial dilaton determines the string coupling. And this tree-level superpotential doesn't depend on the Kähler moduli. And then the non-perturbative superpotential in general can depend on all moduli, but we can focus on a very particular kinds of non-perturbative superpotential, say Euclidean D3 brane generated non-perturbative superpotential, which depends on Kähler moduli at tree level. So the form of the non-perturbative superpotential generated by the ED3 instanton scales like e to the minus Kähler moduli times the one-loop factor. And now the observation of KKLT is that, okay, we want to stabilize Kähler moduli, complex structure moduli, and the axial dilaton modulus, and giving them mass and with non-zero VAV. And the problem is that, as you can see, the tree-level superpotential doesn't depend on Kähler moduli. But if you want to stabilize Kähler moduli in a regime of the moduli space where you retain some control, you want the Kähler modulus to be quite big. And then at the same time, because the tree-level superpotential doesn't really depend on Kähler moduli, you want the tree-level superpotential to be competing against the non-perturbative superpotential. Then here's the puzzle. You need to stabilize complex structure moduli and the axios dilaton such that the vacuum expectation value of the tree-level superpotential is as small as the non-perturbative superpotential when Kähler moduli are large. And then you can, at the same time, stabilize Kähler moduli. And there are many ways to stabilize all those moduli, but if you stabilize those moduli by preserving supersymmetry, then you'll find a supersymmetric solution with the negative cosmological constant, which is where the CC is as small as roughly the non-perturbative superpotential. Hence, you'll find an ADS with exponentially small cosmological constant, hence establishing large-scale separation. Now, as a proposal, this is a great proposal and a great observation, but the problem is that what the proposal is saying is that you need to find a vacuum, a flux vacuum, in which the vacuum expectation value of the tree-level superpotential is as small as the non-perturbative superpotential. So this somehow requires a high degree of fine-tuning. And then this is the very first step to realize the KKLT-like proposal. And then it has been so difficult to find even a single flux vacuum in which the flux superpotential is exponentially small. So for almost 20 years, or maybe 15 years more
20.
precisely. Yeah, yeah. From I think KKLT was proposed in 2003. And
Mhm.
then almost for 15 years, there was no understanding of how to actually find such small flux potential. And
Right.
then people drew in very impressive like machine learning algorithms and big clusters, and they couldn't still find any small flux potential. But what really changed was that in 2019, me and my collaborators, Mehmet Demetres and Liam McAllister and Jakob Moritz, we actually found out that if you look at a very special corner in the complex structure moduli space called the large complex structure point, you can write down the flux potential in terms of some polynomial in complex structure moduli and plus some exponentially suppressed terms in complex structure moduli and exodolaton. And one thing I should stress is that the tree level the flux superpotential is the tree level superpotential, and despite that I can write and the you shouldn't confuse the fact that the tree-level superpotential is written in terms of polynomial plus exponentially suppressed terms doesn't mean that those exponentially suppressed terms are actually instantant corrections. Well, they have some interpretations of the instantant corrections, but at least in type 2b, they are not. But anyhow, what we realized is that if you choose a very particular fluxes in some carefully chosen orientifolding, the the polynomial part of the flux superpotential can be canceled exactly. And what you're left with is the exponentially suppressed terms in the tree-level superpotential. And then once you only have exponentially suppressed terms in the tree-level superpotential, then it's quite natural to expect that the the value of the flux superpotential, once you actually stabilize all moduli, the value of the flux potential will be exponentially small. So it's a great starting point to actually engineer something like KKLT. So that was
Right.
in 2019, but it still took us 2 more years to really get a realistic, well, an actual KKLT solution. The reason is as follows. The Calabi-Yau manifolds come with many moduli, and typical Calabi-Yau threefolds have order 100 moduli. And due to some computational reasons, when we stabilized complex structure moduli to find small flux superpotential, we had to choose a Calabi-Yau with small number of complex structure moduli. And when you do that, what happens typically, statistically, what happens is that the number of Cala moduli is so big, really, just too big. And here's the challenge, here's the technical challenge. Now, if you have a large number of Cala moduli, it means that there are so many force cycles in the Calabi-Yau manifolds, which can be read by Euclidean D3 instantons or D7 branes. And then what you want to make sure is to compute. So what you want to make sure is the following. Whether or not the Euclidean D3 brane wrapped on the force cycle can generate the non-perturbative superpotential is determined by some topological properties. In the absence of the fluxes, they are determined by the structure shift cohomology, and you need to compute the structure shift cohomology of the cycle wrapped by Euclidean D3 branes. Of course, if you have fluxes, then the story will be more complicated, so you need to be more careful. But the upshot is that if you start with the Euclidean D3 branes wrapped on some cycle whose structure shift cohomology is such that the number of fermion zeromodes on the Euclidean D3 branes is just 2, then even if you turn on the fluxes, there is not going to be any new fermion zero modes, so you can use them to generate the non-perturbative superpotential. And now what you need to do is to take in those topologically complicated Calabi-Yau manifolds, yes, and compute the structure shift homology for sufficiently many devices or force cycles in the Calabi-Yau. Of course, you don't want to do that with hands. It's going to be painful. And then write down the non-perturbative superpotential for given choice of an orientifold with the flux superpotential. And now you have the potential. Now, this is not the end. What you need to do is the following. So this potential now depends on, say, 100 kilomoduli. Now you need to minimize it. So you need to minimize the potential in a 100-dimensional moduli space.
Yeah.
And that's also a big, big, difficult problem. And my collaborator, Andreas Rios Tascon and Mehmet Demetas, they're really amazing. They found a way to actually minimize the potential in such a high-dimensional moduli space. So eventually we found many, many minima in the potential. And then now we're finally ready to stabilize all moduli, exoskeleton, complex structure, and Keller moduli. And then,
So wait, so one thing. So did you, when you calculated the minima of this potential in this, 100-dimensional moduli space, did you calculate the second derivative and actually found the minima, or just calculated the extrema and assume that probably they are minima?
uh, oh, so what we actually did was so the potential that we wrote down is the F-term potential, and then we wanted to find supersymmetric minimum, so that we just calculated the F-term, and we solved the F-term equation, and then we just ensured that there is no tagging.
Oh, okay, I see. That makes sense.
Yeah. But anyhow, once
Mhm.
we have all the tools ready, with a big machine behind us, we just ran the scan for quite a few months, and we found some nice solutions. And yeah, that's how we wrote the paper.
I see.
Sorry, it was a long answer. I'm not sure if I answered your question though.
No, no, I think you did. I mean, you used jargon. That's fine, but you did explain the procedure that you used. So this whole thing that you are describing, correct me if I'm wrong, but I think it's correct to say that this whole thing is the first step of KKLT to find the
Yeah.
ADS4 solution with the negative cosmological constant.
Yes. Yes.
So can you do the second step now and uplift it to de Sitter by using some throat and some anti-DD3 brain? Can you do it?
Yeah. Great. So, to really unlift to visit the door, a few more things that you need to do.
Mhm.
The first thing is that when you're stabilizing complex structure moduli, you want to stabilize complex structure moduli around a very special point in the moduli space called the conifold point. And then if you stabilize moduli around the conifold point, actually your Calabi-Yau looks like a long thin cone attached to some bulk, some ball or something. And this long cone region is called the Calabi-Yau electrode. This we know how to do. And also, if you just assume that the tree-level answer that we know and we know how to write down, I mean, tree-level part of the effective action, and then if you just use that tree-level part of the effective action to stabilize complex structure moduli, Keller moduli, exoskeleton, we know how to do it. Now, of course, there are many concerns about the Cleveland structural throats. I can talk about that later if you're interested more. And now the problem is that you need to put an anti-D3 brains into the tip of the Cleveland stress electrode, hoping that
Mhm.
it will not destabilize everything. And this part is the problem. Um, the problem is, well, simply speaking, the problem is that anti-D3 brain, when you put the anti-D3 brain in the Raman flux background, is not a stable configuration. So it will become unstable, and then it will decay or it will find another stable configuration where it will decay into a supersymmetric configuration.
Right.
But the simple point that should really emphasize is that we don't exactly fully understand exactly when this anti-D3 brane configuration can be made metastable. Like, we don't know exactly what the numerical bound on the flux quantum or the curvature of the local region is that makes the anti-D3 brane configuration metastable. And the reason why we don't fully understand this yet is that first, it involves some strong coupling behavior, strong coupling in G string. And also at the same time, as the anti-D3 breaks SUSY, we don't have
Mhm.
many tools, many good tools to really understand this problem. So to answer your question, can
Mhm.
we find the unlifted solution? If you just ignore all the potential corrections, for sure we can. But I think the point is that can you really find a solution in which the uplifting is done properly with the understanding that the corrections to whatever quantity that you might be worried about are all under control? I think we're quite far from that.
I see. I see. So one more aspect that you need to achieve if you want something which is a realistic vacuum is something called scale separation, which where you mean that the small dimensions are actually small, as compared to the
Hmm.
large dimensions. So in the vacua that you constructed with your collaborators, the difference between the scales was something like 10 to the power 100, which is almost a Google. So what I wanted to ask you is that do you think that this is realistic? I mean, yes, separation of a Google, or is it
We're
more than you require?
realistic in what sense?
I
Realistic
mean,
as in
for example, what I'm saying is that um, I would naively think that I would naively think that the scale separation parameter should be so small dimensions should be of the order of a Planck scale. That's what I would naively think, or probably something like that. So based on that, I think the factor of 10 to the power 100 isn't that a lot? That's why I was asking that is it realistic or not?
oh yeah, well, yeah. So I guess by realistic you mean is it phenomenologically realistic, for
Yes,
example?
yes, that's what I mean. Yes.
Yeah, well, our solution was a proof of concept, not
Hmm.
we're not really aiming to find a phenomenologically realistic solution. For sure,
Right.
if you look at the gravitino mass is too light,
Oh,
and
okay.
the moduli fields are also too light. So
Hmm.
the solution that we found can never be phenomenologically realistic solution in terms
I
of
see.
cosmology. And then also the particle physics content is really weird. The only gauge group that is in our solution is SO8.
Right, 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 right. But do you think that if you choose a different Calabi-Yau manifold, that will give you a more realistic solution? There, the scale separation ratio should be realistic. Otherwise, it's not a
Uh,
viable solution.
yeah, one point I should really mention is that just having the reason why I stress that the solution that we have found is not realistic is because
Hmm.
the gravitino mass and the moduli mass scale are unrealistic to be any cosmologically interesting solution. Um, so just having some separation between the Planck scale and the CC doesn't mean that the model is not realistic. Actually, we need the
Hmm.
separation between the Planck scale and the CC to be a phenomenologically realistic model. I think the challenge is then, well, can you also put the mass of, can you also stabilize moduli such that moduli mass are well above Hubble scale, for example, and then, the gravitino mass are well above whatever the experimental threshold is. I think that would be more difficult, but at the same time, I don't see any fundamental obstruction. But to search for such solutions, I think one might need to find new mechanisms to find flux vector. But at the same time, I really don't see any fundamental obstruction.
I see. So another field where you have worked is string field theory.
Yes.
And one thing that I want to ask you is that, so if you look at the community, a very small number of people work on string field theory, but that's fine. But the thing is that a very small number of people actually know a lot of details about string field theory. So first of all, do you agree with that assessment? And secondly, if that's true, what reason do you think is the cause that a lot of people are not learning string field theory? Do you think that they don't have to learn it? That's why? Or is there some other reason?
Mm, yeah. Indeed, it is. Well, I think the number of people who are working on Walsh string theory is small to begin with, and
Sure,
string
sure.
field theory is even smaller. And I agree with your first question. I think that's a fair statement. And the second part. So I'll be honest. I think string field theory has a great potential, but a big problem with string field theory is that it is just too cumbersome to use. I don't think anyone will disagree with that.
Hmm.
And given that string field theory is too cumbersome to use, if anyone is going to use it or study it, there needs to be a good reason. Well, of course, people can just study string field theory for the sake of studying it to better understand the structure behind it. But really, for people like me, for example, I was an outsider to string field theory, and I really thought there's no way that I'm going to use string field theory, at least during my PhD. The reason is that, at least during my PhD, it was not really clear what question I can answer with string field theory, despite that string
Hmm.
field theory is probably too cumbersome or too difficult to use. Of course, that impression was naive and wrong. I think there are many problems in string theory that cannot be addressed otherwise, although string field theory, as we know, is just a perturbative reformulation of string perturbation theory. Um, so I guess what I want to say is that to many people, it's not clear why they need to use string field theory. I think that's the fair statement because most of the things that you can do within EFT, well, okay, most of the things that you can do with string field theory to answer questions about EFT of quantum gravity, you can well do it using just EFT, most of the cases. The reason is that string field theory is not really yet a non-perturbative formulation of string theory, and we can only do perturbation theory, and practically is not really much better than doing some EFT, except for some special cases. Yeah, maybe I was being too harsh, but I think that's a fair statement.
Okay. So I was gonna say that one place, so correct me if I'm wrong, but one place where string field theory turns out to be useful is when you want to study flux compactifications in using Ramon fluxes. So
Yes.
don't you think that that's one area where people can use string field theory a lot, and that's one motivation to, learn string field theory?
Yes. In fact, that was why I started to spend more and more time on string field theory. But I think, in principle, I agree. I think there are many, for example, the problems like, can you compute this correction? Can you compute that correction? And can you compute this number for me? I think most of those problems are too difficult to answer within the formulation of RNS. And the only formulation that we know how to do with those are either pure spin-out or string field theory. So,
Hmm.
given that we have tools and given that there is a complete set of prescription for string field theory, I think we should just use string field theory to compute those without just keep asking the same questions over and over and over again for 10 or 20 years. But I think, as I said, string field theory is just too cumbersome to use. The formulation is not really convenient. So it really requires a lot of time and hard work to even produce the results that people already knew back then, and to get new results, you need to work even harder.
Hmm.
And at the end of the day, you will find some number. I really think getting those numbers is important, but for many people, maybe it's not really worth the problem.
Right. So I just realized that I should have asked you a question earlier. For the audience, can you describe what is string field theory, first of all? Because a lot of them may not be familiar with what it is.
Yeah. So string field theory is a very ambitious research program. So what string field theory aims to achieve is to formulate string perturbation theory or string theory of shell.
Hmm.
And if one can become more ambitious, it also aims to formulate string theory non-perturbatively. Although I think realizing that dream would be probably very difficult. But anyway, so what string field theory does is the following. You start with some background in string theory, and you compute off-shell amplitudes, and you construct some action for excitations of string. And then with the constructed action, now what you do is to directly quantize them. Very much like directly quantizing gravity and higher spin fields, but now with the rules given by string theory. So it's not really that different from string QFT in a way. It's just that you use string theory to produce a reasonable patent call for perturbative gravity and perturbative excitations of strings. So if you think of this way, we're not really doing much with string field theory. Um, but even the simple idea of rewriting the patent call of graviton using the rules of string perturbation theory actually led to many insights, like the unitarity of string perturbation theory and some local background independence of string perturbation theory or string theory and Raman backgrounds and the instantons. Of course, a very unfortunate thing and a very disappointing thing about the current status of string field theory is that it doesn't really do much more than string perturbation theory.
Hmm.
The reason is that when we write down the action of string fields, what we do is to just chop off the moduli spaces of punctured Riemann surfaces into the so-called vertex regions that represent some terms in the action and some Feynman regions.
Hmm.
And then that's it. That's the only thing that we do. And the thing that was special about bosonic open string field theory was that Witten was able to figure out a way to chop out the moduli spaces into uh, in a very special way so that you can basically write down the action of open string field theory in a cubic form.
Hmm.
And once you have that finite structure, once you have that compact of an action, then now you can do some non-perturbative calculation. But in the case of closed string field theory or supersymmetric field theory, string field theory, we don't have that kind of a nice choice to chop off the moduli space. So at
Hmm.
this point, the only thing that we can do is to better understand, in a way, string perturbation theory using the rules of string field theory. But I really think what we are missing is how to, you know, understand some relations between different bits of the moduli spaces.
Right. So correct me if I'm wrong. I remember that when I was interviewing Harold Urban, who also works on string field theory, I came across this conjecture by probably by Ziobeck and some other people that if you add an auxiliary field, then you can do something for closed string theory, what Witten did for open string theory, open string field theory. Is that correct?
I'm not sure if there was a very clearly stated conjecture due to my
Mm-hmm.
ignorance, but I think that's a reasonable thing to expect. Well, reasonable thing to hope for.
Mm-hmm.
The reason why I say this is that let's just forget about all the high excitations of string theory and then just look at graviton. And I think I saw a paper by Grant Raman and his collaborators actually writing the perturbative action of gravitons derived from Einstein-Hilbert action in rewriting the whole thing in terms of a cubic or a very compact action by just introducing more and more auxiliary fields.
Okay, I see. Okay.
And so, although I don't have a concrete reason to expect or to argue for the same thing happening in closed string field theory, but given that we already have uh, a case in at least perturbative gravity with only Einstein-Hilbert action, this is a reasonable thing to hope for. But
Mhm.
I'm not sure if there is any concrete reason to believe that that must happen.
Right, right, right. Okay, so although we use, when we study, string compactifications, one very popular choice of manifold is Calabi-Yau manifolds, and we have talked about them, a bit in this, session as well. Um, so although they are used a lot in maths and physics, we don't understand very well how the metric of Calabi-Yau manifold looks like, right? And a lot of people have done numerical studies to produce something like numerical metrics on Calabi-Yau manifolds. So you had this paper, I think, I don't remember the year, probably last year in November,
Yeah.
where you used machine learning methods to produce some Calabi-Yau, metrics, but they were numerical. So I wanted to ask that where did the machine learning thing help you in producing that work?
Yeah, so I'm not an expert on machine learning. Actually, the heavy lifting was done by Tom Harvey and Kit.
Hmm.
They are the experts on the machine learning parts of the Calabi-metric. So, one I might say turn out can turn out to be completely wrong. So you need to take it with a grain of salt. But as
That's
far as
fine. I
I
mean,
understand,
even
yeah.
if you don't produce the details of what the machine learning thing did, you
Hmm.
can at least explain what. Okay, so if you can explain in as simple terms as possible that what is the procedure to produce the numerical metrics, and in what part in that procedure is helped by machine learning. At least that would
Yeah,
be
so
interesting.
roughly speaking, the thing that you need to do is to solve Monge-Ampere equation. So
Hmm.
Monge-Ampere equation is the equation that hmm, is basically the equation that relates the holomorphic tree form to some other quantities like the metric or something. And once you solve this Monge-Ampere equation, then as Yau's proof shows, there is a metric that solves the Ricci-Flat equation. So one thing you can do is to just solve Monge-Ampere equation, but the problem is that Monge-Ampere equation is a very complicated equation to solve with pen and paper. For one, although we know in principle how to write down the global form of the Monge-Ampere equation, to really use this to get the value of the metric in each coordinate chart of the Calabi-Yau is a technically demanding thing because, for one, there are just too many coordinate charts in the Calabi-Yau, and then when you are solving Monge-Ampere, you want the metric to be complex scalar, and there are just so many different choices for the Kähler metric or the Kähler potential. So the way that the machine learning comes in is to actually help you tune the parameters in the Kähler potential that can solve, say, Monge-Ampere equation very efficiently. But this is my very limited understanding. I actually don't know how things work in great detail.
Right, right. So one thing is that, so my question may be naive, but this is something that I want to ask. So when you write down metric on a curved manifold, you may have to divide that manifold into different charts and write down the metric in different charts, and then write down the transition functions if there are overlaps between the charts. So can you tell us that how many? Do you know that how many charts did you have to divide the Calabi-Yau manifold into?
Oh, well,
Is it a lot?
well, it really depends on which manifold that you're working
Okay.
with. Usually, the number of charts usually scales with the number of calomoduli, but I don't really recall exactly how many charts that we used. Yeah.
Okay. I mean, for example, are you aware of, let's take a very simple Calabi-Yau manifold, something like K3. How many
Hmm.
charts would you need for K3? Are you aware of that?
Unfortunately, no, I
No,
never
I
actually
just want to
worked
gauge the
on.
I just want to gauge the difficulty of the problem that okay, how hard is this problem for like simple Calabi-Yau manifolds? But that's fine. That's okay.
I think if you
Okay.
want a crappy numerical precision, you don't even need to use a machine learning though for simple Calabi-Yaus. That's my
Okay.
understanding. Like
I
10 to
see.
the minus 3 precision, then probably you can just use your laptop without using machine learning. I think
Right.
I think there was some very nice early work by Matt Hedrick and other in mid 2000 and yeah, to really reproduce them, their results, you don't really need machine learning.
I see.
They're like early results, for example.
So are you aware of the structure or the architecture that your collaborators used? So was it just a neural network or was it something else like CNN or RNN or something like that?
I'm really not the right person to ask this
Okay.
kind of a question. Yeah.
Okay, it's
Yeah.
fine, no problem. Okay, let's go to another question that I want to ask. And I think that's one of the questions that you have listed on your website, that this is one of the questions that you are very interested in. And I mean, I would be surprised if any string theorist is not interested in that question.
Hmm.
So the question is that what are your thoughts about the ultimate answer to the question that what is the full non-perturbative definition of string theory?
Well,
I mean, how close do we think we are to the answer to this question? Are we even close?
I don't really know how to gauge the distance from us to the final answer, really. The
Mhm.
only feeling I have is that we're quite far.
Okay.
We only know very small bits about this theory. We know some corners like heterotic string, 11D supergravity, type 2 string theories, type 1 string theory. But really, the big problem, you know, when you're writing a theory, when you're writing down a theory, usually you need an organizing principle. For example, if you start from perturbative gravity and then you wanted to guess the structure of non-perturbative Einstein-Hilbert action, like
Mhm.
not perturbative in the gravity, weak field expansion, I'd be very surprised if you can just guess the structure of the Einstein-Hilbert action by just doing more and more perturbative calculations. You need more input. For
Mhm.
example, you need to understand the symmetry structure or some organizing principle. I really think we do not know what that is. Of course, some naive hope that I have is that, for example, string theory or string perturbation theory is famously asymptotic. And by that, what I mean is that by doing more and more perturbative calculations, we'll understand more and more about what kinds of non-perturbative effects that we need to include, and then that might lead to some hints. But that is a very naive hope that may not realize at all. So what I really think we should try to understand is an organizing principle that underlies the formulation of string theory. But as far as I'm aware, I really don't know what
It
that
may
would
come
be.
off as a bit of a naive question, but I mean, the procedure that you are describing, of course, that will take a lot of effort and it may take a lot of time to, solve, to get the answer to the question that what is the full non-perturbative definition. But a lot of people are more hopeful because they think that the answer can come from holography. And what do you think about that? Because holography gives you, some handle on non-perturbative physics.
Well, personally, I want something more than holography. Yeah.
Okay.
So by that, what I mean is the following. Of course, you can just
Mhm.
take the view that holography gives you the definition of quantum gravity starting from field theory, but I
Mhm.
want a standalone definition of quantum gravity. Holography started as a duality, the duality that relates the quantum gravity to field theory and vice versa. But yeah, what I'm really hoping is that there are two separate definitions of two well-defined theories, one field theory and one quantum gravity. And then we have, in addition to it, some duality like holography, ADS-CFT. Then I think that would be the very hopeful situation. And I really think the holography may not be sufficient. Well, the holography as we know it may not be sufficient because, as you know very well, ADS-CFT requires that the space-time must be asymptotically approaching the ADS.
Right.
And that's a severe limitation. I think many people still hope that we'll find a background independent formulation of quantum gravity. And to do so, we should also be able to change the boundary conditions,
Hmm.
your formulation. Or, yeah, some people may not agree, but yeah. So, well, I cannot really give you a coherent answer or a very concrete answer, but I am hoping to have something more than just holography in a
Right,
simple
right,
time.
right. Okay. I see. So I have two more questions, and then I have some questions from the people, and then we can wrap this up. So
Sure.
one question is that, wait 1 minute. So yeah, one question is that, do you have any advice on how to build collaborations during your PhD? Hmm.
Oh wow, that is a difficult question. I still don't think I'm really good at building collaborations. But,
You're better than many.
my experience is that if you have a problem that you want to work on, if you have a question that you're interested in, that you really want to answer, and then you think having some knowledge or having some expertise will help you answer the question. And then
Mhm.
if you think that some people have the expertise or the required knowledge, my experience is that just sending an email or sending a message to those people often lead to a
Yes.
very fruitful collaboration.
Right. But this email, this thing that you're talking about, that you can just send email to, people whose expertise you require. Do you think that in that email you have to have the whole idea fleshed out, so to expect a reply from them, or even if your idea is half baked, even then you can send an email? What do you think about that?
Um, mm, when I sent those emails, I
Hmm.
usually didn't have fully formed ideas.
Okay.
And when I send emails, of course, most of the times people will not respond, and some people respond with
Yeah.
the suspicion or skepticisms, but sometimes I get lucky.
Hmm. Yeah.
And sometimes you find people who are willing to develop your ideas together. If that happens, that's great. And sometimes you'll find people who'll explain why they think your ideas will never work, for example.
Hmm.
So
Which is
that's
good
also
for
helpful.
you,
Yeah.
right? Okay, I mean, so what you're saying is that, because I'm asking this question because a lot of people think that in order to build collaborations in your PhD, you have to solely um, depend on your advisor. You don't agree with that, right? Or do you?
Well, that's well, in an ideal society, in an ideal world, advisors should act as advisors,
Hmm.
not as your boss.
Sure.
Yeah. So in that case, yeah, you should seek out advice from your advisor, and then explain to your advisors about the problems that you're interested in, and you seek out help and advice. And if your advisor cannot give you the required help and guidance and advice, then yeah, sure, you should seek out some external help. Um,
No, I think I didn't explain what I mean. So what I mean is that you should expect your advisor to introduce you to collaborators. That's what I mean.
oh, I think it's a matter of choice and it's a matter
Hmm.
of personality.
I see.
Uh, like if you're a shy person and then you don't feel comfortable reaching out to people on your own and cold emailing some people that you have never met before, then maybe you can ask your advisor to introduce you to the other people. But in my case, I know no shame. So
Sure, I understand. I mean, when I send emails to people to come to my podcast, I mean, I have to kill my shame to some extent because
yeah.
otherwise it's hard for me to send emails like that.
Yeah.
Okay. Another thing that I want to ask you is that actually I have two more questions. I said two
Mm.
questions, I had three questions. So another question that I have is that so the time that you have spent doing physics, in that time, using all of the experience that you have gained, can you give some advice on how to choose a problem to work on? Because you may choose a problem that is too hard. You may choose a problem that will take a lot of time. So, are there some things that you have in mind when you are choosing a problem to work on?
I am actually not good at doing that.
Okay.
But I can tell you what I do. I
Mhm.
am very easily obsessed about a very few particular problems. And when I get obsessed over those problems, I cannot just let them go. So what I typically do is to try to break those problems down to bite-sized problems. Sometimes it works, sometimes it doesn't work. If it works, you have a big problem and then you really want to solve it, you really want to answer this yourself, but it's usually too difficult to answer at once. So what you do is to come up with some simpler version of the problem or some smaller problem, and then answer those simpler and smaller problems. And then whenever you have time again, you go back to the big problem and think about the problem again, and then think about whether or not you can come up with now a bigger problem or more complicated problem that is more similar to or more closer to the actual problem that you want to solve. And then you just
Mhm.
keep doing that again and again and again for many years. And actually, there is a problem that I really, really wanted to solve and I still want to solve. And I've been doing this procedure for almost 9 years now, and I think I'm getting more and more close. So this is what I do. Yeah, but I'm not sure if this works for everyone.
Mhm.
And yeah, but anyhow, if you have some obsession, I think this might work.
I
Yeah.
see. I see. So, okay, one last question that I have, and I will ask that, and then I can go to some of the people's questions.
Mhm.
So, one problem is that, sorry, one question is that on your website you have this thing called CV of failure.
Oh yeah.
How did you get that idea to make something like
Oh,
that?
it was not my original idea. I think I
Yeah,
was
but how did
reading
you get the
some.
inspiration?
I think it was a good thing to do.
Hmm.
So I a news saw one news article describing an academic who has listed their severe failure, and I thought that was a good thing to do because as you grow old, especially if you have certain things that worked out for you, you can fool yourself as in, okay, I did so many great things and I'm here. But at the same time, one should not forget that for most of the people to have a success, you need to go through many failures to arrive at that point. And remembering that and be willing to fail again and be willing to make more mistakes again, I think that will be actually quite important to have some life or career or whatever that can last happily without going insane. So I thought that was a great idea, and I thought I'll also document my failures.
Do you think that if more people, more accomplished people start to do it, that can help younger people to realize that failure is a normal part of your journey? Because a lot of people
Uh,
tend to hide their failures.
I'll be honest. I think younger people should look at accomplished people as they should listen too much. They look
Mhm.
up to their heroes too much.
Yes.
And they, in a way, I think, worship their heroes to some extent. I think that's really bad. So I really think what younger people should really do is instead of looking at those accomplished people and what they're saying and what they're doing, just to look at themselves and be honest with themselves and then think about what they want to do. And
Mhm.
if some failures are necessary to do what they want to do, then just,
For
go
sure.
on with it.
Right, but what I'm saying is that um, if a particular person is trying to achieve a goal, and if that person has a small setback, a lot of people tend to think that, okay, it probably means that it's not meant for me to do this particular thing. But if you know that failure is part of the any person's journey, any successful person's journey, then that setback may not give you the idea that, oh, it means that you're a failure, right?
Yeah, that's a great point. To be honest, I'm not also very good with dealing with failure. Although I
Mm.
say I talk as if I'm so over the failures, I'm actually not good at dealing with failures. That's why I do all kinds of things like writing a CV of failures, because when I face a failure and then when I don't get things that I really wanted to get, my heart is actually my heart is broken quite badly usually, and I have
Mhm.
many bad days, and it takes time to really get over those failures. And I also oftentimes have the thoughts, oh, maybe this is not for me, maybe I'm too dumb, or maybe I'm not just good enough. I have that thoughts many, many, many times. Um, but really, at the end of the day, it boils down to your personal choice.
Mhm.
It could be that, yes, you're not actually that good. You're not good enough and you'll never make it, and then you need to give up. It can happen, right? We never know because
Yeah.
we cannot really predict the future. And or you can be very lucky and eventually if you try many, many more times, you'll eventually succeed. So I think at one point what you really need to decide is whether or not you want to take a bet. You want to risk. And I think that is really important.
Hmm. Right.
So it's really your personal choice. And there is no answer or formula for when to stop and when to keep going.
Okay. So I have some questions from the people. So let me ask you those questions. I think the first question is a bit related to what I just asked you. So if you want to add something to that, you can. So the first
Sure.
question from the people is that during working on any solo project, when you feel stuck sometimes, or feeling of rushing sometimes. Sorry, I think the question wants to ask that, do you feel stuck sometimes, or do you feel like you're rushing sometimes, a feeling that you are not good enough for something, and you quit the work and switch to something new? I mean, it's not very worded very well, but this is what they want to ask.
Mm, yeah. Well, for sure, I get stuck all the time. I
Mhm.
really think my professionality is to get confused. I get confused about the most basic things all the time, and I get stuck at basically every possible step on the way to finish the project. So yeah, the answer is yes, I get stuck every time.
Okay.
But you need to work on a project that will get you stuck. And I really think you need to work. This is what I think. I really think the good problem for you is the problem that will make you feel like you're suffocating a little, but you're not actually dying. So you're
Exactly.
struggling to live and survive, but in fact you can actually do it, and you'll learn something new. So I think feeling stuck is actually a good thing. As long as you don't give up, it means that you are learning something new because obviously if you knew something about this project, you wouldn't feel stuck.
Okay. So the next question, I don't know if you have strong opinions about this, but if you have, you can answer this question. So the next question is that what are your favorite dark matter candidates and why?
What is my favorite dark matter candidate? I really don't have any favorite candidate, I'll be honest. And well, I know that these days people are working more and more towards the fuzzy dark matter and axions, and people are expanding the number of models that they're testing using experiments, which is a good thing. Maybe one reasonable thing I can say is that having fixated on a model is not usually a good idea, especially if a community is fixated on one particular model. Because I really think what we should do in a situation like what we're facing in the theoretical physics and fundamental physics these days is that we don't really know which direction is the right direction to pursue. And we should be more open-minded, and we should be always ready to give up our favorite idea and favorite model whenever the nature tells us not to pursue it any longer. So I think, well, yeah, one can have a favorite model or whatever, but one should also be willing to throw it away when the evidence is strong. And I think having just a few favorite models for a community is usually not a good thing. I think this is what I can say.
I see. So the next question is that um, what is most important for doing a good PhD, a good advisor or a good university with a good research environment?
Ah, that's a great question. Well, I'm tempted to say having a great advisor is very important.
Hmm.
Um, you know, I'm not sure about you, but for many, especially many international students who come to the US, for example, or who go to different countries um, to pursue PhD for many, many years, it's not a very easy choice. You're far away from your friends, your family, and then you're working on this very difficult problem that may not lead to anywhere.
Hmm.
So it's a very challenging time emotionally and academically, of course. And having someone who can understand you and then who can support you through the journey is very important. And I think one of the main roles of advisors is that. And if you have an advisor who can actually support you through this difficult journey, then I think the chances that you'll likely be able to do something not so meaningless. But I think also at the same time, the environment and university are very important, um, both academically and personally. For example, if you don't really like the place that where your university is, you'll probably not have a very good time during your PhD. Yeah.
Hmm.
And also, I think depending on who you meet as your cohorts and your colleagues really, really affects how you view things and what things you know and how you think about certain problems or certain things. So having good colleagues who are brilliant or who are really, sharp is definitely a very important thing. And usually when you have advisors, unless you're very lucky, advisors are usually very busy. So the time that you can interact with your advisor is somewhat limited. So most of the time during in your office, you'll interact with your colleagues. And if you don't have good colleagues, it's kind of difficult to learn, from your colleagues or do something with them together. So although I think having a great advisor is a little more important, I really think as well, having a good university and good colleagues and good environment, they are probably equally important. So I'm not sure exactly how to argue for the, more important, argue that something is much more important.
Sure. Sure. Okay. So there are two more questions, but I think they you have also answered those questions already. One of them is about string field theory. The other one is about
Hmm.
KKLT. So I can
Sure.
just skip them.
Oh,
Uh,
well, you can
s-
still ask them.
oh, okay, sure. So
Yeah.
the one about string field theory is that are there any subtleties in going from string field theory to string perturbation theory that we should know about?
Subtlety? Can you say that again? You said subtlety or?
Subtleties. I mean, oh yeah.
Ah, hmm, subtlety. Well, I think the direction is the other side.
Hmm.
We don't know how to start from string field theory and to go to string perturbation theory. The way to construct string field theory is to start with Walsh's CFT and then construct string field theory. So unfortunately, we only know how to go from string perturbation theory to string field theory. And subtlety-wise, I think the most of the subtlety is related to how to deal with off-shell states and how to deal with all kinds of off-shell data that you need to put in to the construction of string field theory, like the local coordinates and the location of PCOs, etc., etc., etc. Yeah.
I see. So the next question is that I would want to hear his opinion on the status of KKLT. I think you have talked about it, but if you want to add something, you can. But there's a next part to this question, which says that specifically what he thinks of the recent concerns in the context of ADS-CFT.
Mm. Are you referring to
I'm not sure
uh,
what concerns they're talking about, by the way. I didn't write the question.
I see. I'm guessing that this concern refers to the uh, a paper put forward by Vafa and
Wafa, yeah.
collaborators, yeah,
Hmm.
on the ADS-CFT duality for KKLT.
I think there
So
was another paper in 2022 by Wafa and Loost, I think, where they said that the first step in KKLT has problems. So they have
yeah,
been
yeah, that's the
bashing
paper that I
KKLT for
was
a long
referring
time.
to. Yeah, yeah. That's the paper that I was referring to. Yeah. So
Okay.
the idea of the paper is as follows. If you believe that ADS-CFT must work for any ADS string then what you would assume is that the ADS part of the KKLT construction should also have holographic dual, but in terms of CFT. So I think it's a good question to ask. So what is the CFT? Can we construct them and then can we compute any uh, properties of those CFT? Or can we also use this ADS-CFT duality in the other way to learn something about KKLT construction in the bulk? Like, can we rule out KKLT or can we compute some properties of KKLT? So this is a great question that we should think about. And what Conran and company, what that Harvard paper attempted to do is the following. Um, in many constructions that we know about ADS-CFT duality pairs, what people often do is to start with a brain stack and take the near horizon limit and take some parametric limit, so-called the 't Hooft limit. And then by doing so, you find that, okay, there is an ADS-CFT duality pair. So here's one logical step that you can take. What if the dual of the KKLT is also obtained by some notion of near horizon geometry or some brainstem by taking some decoupling limit or something analogous to it to a brain setup that you start with. And then with that assumption, you can think about what could be the candidate brain stacks. And then using that idea, you can try to compute some quantities and properties such as the central charge or the CC of the gravity dual. And here's what Kamran and company found, which is that if you assume that the bulk, so in the construction of KKLT in the bulk, you needed to turn on many fluxes, right? The idea of the paper by the Harvard group was to replace those fluxes with D5 brains and S5 brains, and then you try to understand some CFT obtained by the IR limit of those brain setup. And because this brain setup will break SUSY, in general, there isn't much theoretical control you have, but you can still assume some general things and reasonable things to study the IR limit of those brain setups. And what you find is that, okay, the central charge that you can compute or you can guess for the IR limit of the brain setup doesn't really agree with what one can actually find in the gravity dual. Yeah. So then you can contemplate many possibilities. The first possibility is that assuming that your setup for the ADS-CFT is correct, the bulk solution that we have found, for example, cannot be correct. That is one logical possibility. The other logical possibility is that, okay, maybe this is not the correct setup for the ADS-CFT duality for KKLT.
Mm-hmm.
And so there are two logical possibilities. And the unfortunate thing about their proposal for the ADS-CFT duality of KKLT is that although their idea is a very natural one, if you think about it, usually we construct ADS-CFT starting from the brain setup. So this is a very natural one, but there is no reason to expect that generic ADS-CFT to always work like the decoupling limit of some brain setup, although it can well be. So, and at the same time, they haven't really provided strong evidence as to why the dual of the KKLT ADS must be constructed out of the brain setup. On the other hand, although there are some loose ends in our construction, we did explicit calculations. We did compute the superpotential, Cal potential, and we explicitly minimized the potential. So as far as the computations that we were able to carry out, I really don't see any problem. And usually when I'm confronted with, like, do you trust an argument or a computation, I usually choose a computation because, language is a fuzzy thing. Sometimes you can fool yourselves if you really believe in something, especially with the arguments. But computations don't lie. If you find some results with your computations, even if you don't like the result, you have to really follow it. In fact, I really don't like the idea of the entropic principles and the landscape and whatnot. So, I understand why people sometimes don't like the constructions like KKLT, but the calculation is calculation.
Mm-hmm.
So I would say that I think the evidence, circumstantial evidence, favors the bulk construction more. But of course, I'm not trying to imply that our solution or our construction is free of any criticisms. If I think a better criticism would be that there are so many unknown corrections that we didn't compute back then because we're not able to compute them. And then there could be a possibility that the Wilson coefficients of those corrections that we did not compute can be fairly large, and that can destabilize our solution once we
Hmm.
include those unknown corrections. I think that's actually a beta criticism.
Right, right, right.
And if that happens, then we need to throw away our solutions. And although my collaborators believe that that will be highly unlikely, but I literally don't know what will happen. That's why I've been spending my time on computing those corrections.
Sure. I mean, there is a very so there is a claim which doesn't have a lot of evidence to it, but this is something that I have heard from the word of mouth of physicists. It says that okay, so this fact in air quotes is that loving KKLT and hating KKLT is an East Coast West Coast thing. Is it true? If you're on West Coast, you will like KKLT. If you're on East Coast, you won't like KKLT. Is it correct?
Maybe there is some truth to it. When I was
Okay.
brought up in my PhD study, I didn't really like KKLT.
Okay, sure. And now you are at Stanford and now you like it.
I still don't. Well, I I well, to be more precise, I'm neutral about the KKLT
Hmm.
proposal itself.
Okay.
Um, it's unfortunate that we don't have many more ideas to construct digital solutions in string theory, and KKLT remains one of the best studied proposals. So I think it
Mhm.
is very important to understand exactly whether or not it works. And I think the circumstantial evidence is that at least the 80s part is certainly working, and Digita is a little bit more difficult, but I really hope that we'll get to the bottom of that, and then I sure hope that we'll find Digita solutions or whatnot. The thing that I really don't like is the entropic solution to many big problems like cosmological constant problems. So KKLT itself, I have no beef with it, but I don't like some use of entropic principles, for example. And regarding your question about whether or not it's East Coast or West Coast, I think it's more about uh, Harvard versus
Stanford.
Stanford, for
Right.
example.
Harvard and would you include Princeton in the East Coast thing, or is it just Harvard?
Well,
It's mostly Harvard, I
it,
agree.
well, but there is no benefit to like bringing in sociology to scientific
Sure, I agree.
discourse, right? I think we put too much emphasis on sociology and who thinks what sometimes. I think we should completely ignore that. Like, even if some famous people believe something or famous people are proposing something, we should not look at those thoughts or proposals because they're famous, they're the brainchilds of famous people, but just because they're interesting or they make sense. And I think this West Coast versus East Coast or Stanford versus Harvard are not doing any service.
Yeah, I mean that's why I said that this is something that I've heard from physicists, but it doesn't have
Yeah,
a lot of data to back it up.
yeah.
Okay, so last question, and it may be a bit of a depressing question from the people.
Oh, okay,
Uh,
I
the,
like the pressing questions.
the question is that should I still pursue string theory in 2025?
Ah, in what context?
I mean, I think the person who asked this question, I know that the person is a master student and he will start his PhD. So probably
Hmm.
he wants to ask that should I work on string theory in my PhD in 2025?
It really depends on what the motive of the question was. Like in general, I think if you're thinking about pursuing or studying or doing some research in theoretical physics in some topics of theoretical physics just because of the fact that you want to be a career theoretical physicist, like become a faculty and just you just like the title of being a researcher.
Hmm.
I don't think it's a good idea to do theoretical physics anyway, regardless
Hmm.
of what the topic is.
Sure.
And like if you, yeah. if you just want a good career, I think choosing a different discipline or not even staying in academia is usually a better thing to do.
Mm-hmm.
And now, in terms of scientific part, like whether or not you should, well, I guess, it's difficult to answer the question in a very nice way because I don't know exactly what the motive was and exactly in what context the person was asking the question. But if,
Okay,
yeah,
let me clarify. So this is a question that a lot of people, a lot of younger people ask, and the context that I understand is that, so as you surely know, that there is a lot of misinformation on the internet that string theory is dead, right? Things like that. So a lot of younger people think that it's not worthwhile to work on string theory anymore because it's a dead end. So that's why they're asking this question. So in that context, what do you say?
well, if
I know it's funny, but it's sad too. It's
um,
it's sad
you
too.
know,
Yeah.
my rule of thumb is that if you want to work on research
Mm,
that requires you to ask your own question, deferring your judgment or outsourcing your judgment to someone else is usually a sign that you'll not do a good job.
mm,
If you cannot make your own decision, yeah, probably it's not a good idea to do research.
I agree. I think that's a very good, nice way to put it. Yeah. Okay. Let me see if I have some other question. No, I think I'm done. So thank you for your time,
Yeah,
and I
thanks a
hope
lot for
that
the invitation. Yeah.
no problem. I mean, it's my honor to talk to you after following you for a long time, and I hope that we can talk sometime in the future as well, whenever you get time,
Oh yeah,
if
that'd
it's
be
okay.
fun. Yeah,
Okay.
let's do that.
So okay. So thank you for your time today.
Yeah,
Have
thanks
a
a
good day.
lot.
So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.